Start. So this is the last lecture for the whole year. In this last lecture, we will do a kind of review, but for the review, we will check one of the project problem. First, we will do a code walking. Then, if time is left, we will redesign what we have seen as the final output. Okay. So, do you remember the problem? What was the problem? The problem is given a directory structure, a root structure, we want to design a crawler which goes, checks every subdirectories and retrieves, collects whatever data we need to do. So for the case, we just simply want to make a list of files which follows a certain criteria that we need to look at. So that means the crawler will consume a root point in your file system and a predict function, which is the function which decides whether to keep the file or not, or whatever criteria is there. So you can design whatever function you need to have. First, you can check for files that contain some kind of information. You can look at the files which has certain size, or files with certain names, and so on. So it's a kind of crawler. But the idea of that the problem is how can we design such a function which accumulates knowledge on the way when it processes the inputs. When it's done, it returns the output. So that was the question we had. Now I am going to check the solution, but the solution doesn't have any keys or indication of how the design is completed. So that's why we will do kind of reverse engineering to examine how we could end up in that state. The reason we will do is because we want to revise the design stages. So we will do how we would end up in that stage, in that state of implementation, looking at earlier design stages. So that should help us to refresh and summarize what kind of actions we need to take when we do the implementations. So this is, let's open up the file. So first of all, in this implementation, we do indeed use a teach pack, actually a kind of a module that we want to use. As a dir directory teach pack, it allows us to collect data from the directory tree, which we will give a certain path and collect the data in this directory tree. So if you want to check this one, you can always go examine from the header, from the help desk. But the thing is, so there's a predefined, the data definition for a directory structure is already given. This information comes within the teach pack with the module. So we don't have to. That's why we have commented out, because you don't have to define the structure for directory and so on. But if you look at, this is the thing I just extracted from the help desk. So it tells that a structure, directory is a structure. That means you would define structure. It was your own manual design. It has three components: a name, directories, and files. A name is the symbol. Directory is a list of directory structure. Files is a list of file. So, and a file is also again a structure. It has a name, a size, and a content. Name is a symbol. Size is an integer. In kilobytes, I guess. And the content is a list of characters. Actually, current implementation doesn't return any content for it returns empty. And so when there's also a certain function which comes with the teach pack, it's a create dir. So you will give a path, which is a path within your file system, and it will go and collect information about that path and constructs this directory tree structure. And then you can work on this data which is made ready to use. So we can check this Because, for instance, I have created, I check, for instance, this is the line. I want to extract the information starting from this directory and check all the information from its subdirectories. Because for the current directory, we'll get a name and we'll check its subdirectories and files and so on. So we can see indeed what's the directory structure by checking my root. Let's see if we can see that. Yep. So for instance, this is a big directory structure. So we have this is the root directory. Then I have a list of subdirectories, which starts here, and I think it ends over there, and list of files immediately under that directory structure. So that means under the projects file, under projects directory, I do have like 3-4 different files. You see the file names, file sizes, but the content is not retrieved. It stays empty. And for each, under that directory, we have one subdirectory, I guess. Yes. Just one single subdirectory. On this subdirectory, we have another subdirectory. So that means this simple function which creates information you need from your file system. So that was that's the thing. Routine comes with the module we have. But our purpose was, given a directory tree, a path like that one, and a certain function which decides which files or what kind of information we need to collect from this directory tree, and returns it. So what we want to design is that's the design we wanted to have. So if we check this one, so we have a crawler we want to design, which takes a directory, which consumes a file and returns a boolean, checks file whether to keep the file or not, and then returns list of string, maybe list of file names in string. You could come up with different things. So this is a simple, a specific implementation of crawler. So for that one, you need to somehow decide which files you need to keep, and based on the predicate function you do have. So in terms of the things we think we need to keep, we will design an accumulator, and we will use this accumulator to update the information. So what we have here is really just the contract of the whole design and nothing else. So that's what we are going to discuss together. What part of this final implementation reflects which part of the design and so on. So if we check this function, I will see it completely. Yeah, this is the whole function we do have for the crawler. So that means it has local definition. It has two functions inside, and then it just starts. It gets the current directory, a predicate function which is also input, and then starts with an empty thing, with a value. So, for instance, looking at this implementation, would you recognize that there's a design of an accumulator here? And this will imply that the accumulator is initialized with an empty. So, and the function calls crawler, and this is the function. If you check this one, you will realize that the data type of accumulator is string. But since we don't have a complete design, we have no idea what that accumulator represents. So that means we know that how it is initialized, we know that what the data type it has, but we don't know at the moment what that accumulator is going to have here. So do you have an idea, looking at the code here, what that accumulator might stand for? What might it represent?
List of string.
If you check this one, it's just a string. The data type is a string. So what can that accumulator hold? And in order to look at this one, we could check Or sorry, so that means there's a problem with this representation. So this is, you can't just initialize something with empty as a string. If that means we need to update, this is file, this is the Boolean directory, and we don't have anything else. So the accumulator is a list. That's what you have suggested. It's a list of string. Then now we go back and see what that it stands for. We have initialized as empty. It says it's a list, and that means we need to check the contract. It's important how important is the contract is to be able to see it. So we had that, probably there was another something wrong with that we didn't use it, or it wasn't useful at the moment. So what that list might keep, actually, if you look at the design, what that it represents. Yeah. So accumulator. What are we holding? Why do we need an accumulator? What's the use of accumulator in this case? So this is the path. Yeah. We will keep the actual file paths, whatever. So that's the thing. How we can understand that, because that will be decision in first place. What we are talking here is a completely reverse case. That's why we are trying to re-engineer what we have done earlier. So in this case, what accumulators is used it does represent list of files that we have kept while we were crawling the directories. So that's the representation. And what point of the implementation you see that the accumulator is updated? So yeah, if you check this one. So let's forget then. It looks like it gets more complicated than we were expecting to do the reverse engineering. We could go and say if that was the function we decided to use, and we decided to tell that accumulator is a list of strings and stands for files we decide to keep. So and in this case, this is the accumulator we do have. So if you just consider the function, if you're up to design the function, would you start thinking that this is a generated recursion? It requires a generated recursion approach, or is it it's completely structured recursion? If you forget about the code you have seen, what would be your decision? So you do have a directory tree at a certain point, and what you want to do is check the files under the directory tree, because it comes with the structure. You have a list of files. You want to keep the ones you need and do further recursion. Tell your crawler, go do the further recursion for each subdirectory. So what will be the template of this function? If it's you can think of generated recursion. It will end up structured recursion if you don't need an advanced algorithm. But if you check the nature of this problem is, you need to check every single file, and then you need to do recursion for each subdirectories. So that means you would actually, and the data you consume is a directed structure. So what you need to do, first of all, open up the data you have. So you would extract this is actually, if you check this one. So for the template, you would say, well, let's have this as we had. So if you want to do the template for this one, you need to open up this is the directory structure. It has dirs because you can always check what are the what are the fields, it has name, dirt, and files. That will be a simple structural template where you extract data from each one of them. So that will be the first thing you would do. So that you will say, I need to take maybe the name, just follow of this current directory, and then you will do the subdirectories, and you would also extract files, I guess. Or was it so? Yeah. So that's the thing you would need to do. Now having opened up data, this is a simple template you could go. What you end up here is as a symbol, because we know that data type is symbol. What you have is list of directories, and what you have here is a list of files. So now it's actually that would imply that you need a function which consumes a list of directories and keeps collecting data from subdirectories. And also that means this is again compound structure. You need a function which extracts the files which fits into your criterion. In this case, we have single predicate function. Then you will design the solution actually this one is a straightforward function. You can use abstract list processing functions like filter or in order to extract the files you need to have. And then that will be one thing you would have. Other than the current input, we also do have list of files, which is already one of the accumulator. We do have a predicate function. So that's the things you would end up in your template in the first place. So how would looking at this template that helps us it's not completed. We need to have a function in order to work on this subdirectories. We need to have a function, an expression to extract files here. So if you look at the implementation, where do we actually have the files? So this is in this expression, this is the list of files, and you have a predicate function. You could use filter and with this predicate function to extract which files you need to keep. That will return, that will return list of what? Because their files is what? Is a list of structure. So that means you will have a list of files here. But that function would actually keep the files which are, fits into what you have. So this is the initial list of files. You filter. You actually do the filter if you check this thing. So what we have done here is we do have current list of files. This is the current accumulator, and if you check the data type, it's list of strings. So we have actual list of file names, and then you can with this filter thing, so you would extract the ones you need to have. But at the same time, what you have here is you need to add full path of just not the file names. You need to add to the current the absolute file name to the full path. So that map function, which we will do that. So this is how you could update current accumulator. And that will help you to extract the files that you need from the current subdirectory. But now you have multiple subdirectories, multiple subdirectories. It might be empty or not. But the thing from that expression would lead us that we need to have a helper function or another function which checks every subdirectory. But while we go and check every subdirectory, we need to pass on the current information we had because we want to use this accumulator style design. if you check this one, that means this is the function name you have decided. It takes a list of directories, keeps the current predicate function, and updates the current accumulator. So what it does is it adds, because we do have current list of files, then we extract the ones we need to have, and then convert them into the form we need to have, then append them. So this is old accumulator, the data collected so far, and then we filter the file we need to keep, and then update and transform the form, make a structure in the way we want to have, and then pass on to the new function. This is just a simple thing. If you look at the whole design, it's really just a simple template, but you will decide where you need to have another function. So that means you would do the design for this function. In this case, actually, we don't have, again, this string. So we do have accumulator, list of directories, and predicate function. What kind of design you would do this? I mean, if you check this one, it's obvious the structured recursion again, because we need to check every single directory, and for every single directory, if you look at this one, if the list is empty, then the accumulated answer will be the solution. Otherwise, what you need to do is you would keep collecting data from the subdirectories, but before looking at the rest of the file, see how you update your accumulator. You go other function down, and then collect the list of files from under that file, and also under that directory, and all subdirectories under that directory. And then now your accumulator is updated. With this updated accumulator, you will keep self-recursion. So that's a simple crawler where you apply structured recursion with a simple accumulator. Okay. Any questions for this implementation? Again, this is straightforward structured recursion. But what you would do, and what's more important here, how you do update your accumulator. So in this case, actually, if you had A, B, C, and subdirectories, you would collect all the files which fits to your predicate function, and then getting this accumulator, you will go and check the new subdirectories, and so on. You will finish them up. So this is how you would do. If it's okay, now I will go and check its Python implementation, and then we will be able to compare. It's the first time we look at another programming language and see how the same principles applied to another programming language. So the whole design is here. For the complete design, we do have here, and actually, so again, it doesn't reflect the whole thing, but it's again the final implementation. But if you check this one, it's a structure, function, a recursive function, and it's really short. And because it reflects what you have implemented in the in what you had in the design recipe. If you check this one, it again keeps. It starts with a root path, a predicate function as input, and an accumulator. This time, the accumulator is a list. Again, but this list is a Python list. If you see how we have initialized, then you need to see how you have initialized the accumulator. If you check this one, we have initialized an empty list, and then we pass the empty list to the function. And also look at this one. This is built-in function which comes with OS module. In Python, actually, I think you need to import the modules. So this is function which comes with the OS module, and you say okay, I'm starting with the current directory. This starts with the current directory. You could get this from the user actually, or from other files, functions. So you start from the current directory, and you pass on, the function, the prerequisite function. It's a simple function I have implemented here. It uses a more generic function, as you might have seen here. So it's just, for instance, if it's going to collect all code files. That's how it works. So that means let's check how this function is implemented. You have the file name. It takes the file name and it decides whether to keep the file or not, I think. Let's see. So if it's, for instance, if the file name, what it does here is, again, I'm using the module functions. This is the file name. This is, again, comes with the OS module. You have the path. It's another, part of the. This is a function. It's actually a kind of object. It has functions. The path object has a function which splits the file name. So you do have the full path, and then the second part will be dot, for instance, Python, or dot py, or dot rkt. So that's why in this case you select the second component, because the second component will be the file ending, and this file ending starts with a dot and then file extension. So in order to get rid of the dots, you say I'm going to keep the other things, the string other than dots. So that helps you to extract just the extension where the dot is ripped off at the head of the things. So that means if in this this is a particular thing with the Python, that means you can have more than one arguments. If there's more than one argument, what it does is it keeps them in a list. So that's why you can use whether it's in that list or not. So this is a simple thing you can do in Python. So it helps you to check whether the extension is within one of the file type you want to have or not. So that's one simple thing. So now let's go back to our basic crawler. What it does is, so this is again, it checks, this is again like the same idea. You have list of files, you have subdirectories, but it's not like the way we have a design, or it is designed in Rocket environment. In Rocket environment, you have a particular structure where you have directory, list of files, and list of subdirectories. In this case, we use another programming language with another module, but we still can apply this. So we do apply the same principle. The principle is for the current directory, you need to look at the lists and extract the filter out the ones you need to have, and update the accumulator. Once you have updated the accumulator, go do the recursion over subdirectories, each one of the subdirectory. So since we have 4 routines, that means that's the reason. The reason we have a single function is because this 4 routine stands for the second function we had in Scheme environment or in Rocket environment. Look at that one. So that's the thing we do here is to look every single subdirectory. The way it's implemented in this programming language, because you have you have a particular construct, which is for construct. You can use this for construct because for each one of them. So now let's look at how we have implemented. So for each file, so again, that will stand actually for the filter and map implementation of what we have in Scheme environment, and you can do it here actually. So what you do is you check every file in the current subdirectory. This is how you make the full path, absolute path, and say if it is file, if the current thing. We have to remember that what does this function returns. So when the module function returns both files and subdirectories, because directory structure is also principally is a file. It's principally is not so different than a file system component. So in that list you have both files and directories. So what you do is, if it is file, if the current component is a file, then you say if this file fits into your predicate function, you send this predicate function. If it's true, what you do is you update your accumulator, because accumulator was a list. Now you append this item to end of the accumulator. If it is not a file but a directory, then you need to go and do the recursion. It's simply you see it's a self-recursive function. For this file, since now this is like another directory, you would use the same predicate function, and you would keep using the accumulator, the same accumulator. So this is how it is implemented. Simply you check the file if it fits what you need to do, what you need to keep, and you would add it to your accumulator. Otherwise, you would do recursion. So since we have force in a construct here, we didn't need to have separate functions which does mutual recursion. So, but the idea here is we still apply the same principle using accumulator in a recursive function design. Any question about what you have seen so far here? Well, if you really like functional programming, you could do. For instance, you could use lambda expressions in here. So for the lambda expressions, for instance, it's as far as I know, I'm not sure about the things, but I will try the syntax. We will see. So for instance, instead of using the function you have defined, you could define function in place, and then call the crawler. For instance, for this function, we could use keep types, and with the keep types, actually we could implement this in place, which means use keep types with X and with Python, extensions. Keep types this is the function we have defined. I have defined it just for generic thing. So for instance, you can say, well, not only Python, you can also say, well, let's keep the record files as well. So see if it works. I'm not sure if this is how lambda expression works, but we will try. Okay. Yeah, I think it's how it works. See, what we have done is so access directories, and this is the final output. We kept Python files and Rugged files, list of Python files and Rugged files. So you could also use, that means this is the syntax for lambda expressions in Python. So, and one thing, I think it should come with Python as well, which is very powerful. Sorry?
Can I say something?
Sure.
We don't know how we can use lambda in Python, but we can think and we will use it direct Python learning.
You don't know how to use lambda in Python. Yeah, you didn't know. I wasn't sure. Now we all know how we can use it. Because this is.
How can we think we will use their lambda?
Okay, actually, thanks for the question. The question is, how can I come up? There's a lecture here. How can I come up with the idea that I can use a lambda expression here? So this is a nice question. It might be the question we can wrap up the whole approach in this lecture. In this lecture, what we want to do is to be able to get the idea about designing the function program and designing the programs. So the idea here is this is a simple function. This component was, if you look at this component argument tells that I need to pass a function as an input. So if the function you want to pass is a simple function, you don't have to. You might not. You can just define function in place. And the way that means you don't need the name of the function. That means you need a way to define an anonymous function. And in functional programming, this is we have learned from we know the lambda expressions in the Rocket environment. So that should be a way to do lambda expression. I have used it before actually with Python. So then you say, well, instead of using a function name, I can implement the function in place. So that hints us that we need to think about the underlying design process, other than the syntax and so on. So that's why you don't need to know in advance everything, but what you need to know, what kind of thing you need at the point you have. So while actually looking at lambda, then I thought maybe there is actually ways to use map, fault, or filter in Python environment. So for the list, for instance, I think, let's say, it helps. It tells that this is a nice thing about Python interaction environment is that it tells you that, well, you can pass a function and a sequence, and it will produce a list. So for instance, we can pass again a function that we have defined. Let's say we just multiply and take the square, and then the sequence, let's generate a generic sequence. So this is this is how. So we have generated a list of numbers from 1 to 10, and we took square of everything. So that means we can use the idea of abstract list processing functions in many other programming languages. And I think there's also filter. Maybe let's take this one. So let's say we have mapped, and now let's filter what? I'm always going to syntax of Rocket. So yeah, filter takes a function. So let's say again define a lambda function, and if x larger than, let's do simple stuff. Oops. Yeah. Yeah, this is how we can use filter in another environment. So there should be something else we really need to know, which is what? Folder. But I think it's not fold. Let's see if there's fold. It should be reduce. Help. Yeah. Okay, how about reduce? Yeah, there is reduce. So let's see how it works. For it's fold. Fold is implemented as reduce, and reduction because you reduce a list into a value and so on. So for fold implementation, we need to have a list, a function, and also maybe sometimes an initial value where we can. Actually, fold is an accumulator design function. It's sort of an accumulator. So there's two folds in Rocket environment: fold R and fold left. I guess fold left is the accumulator. If you look at the implementation, fold left it uses an accumulator. Fold R is not an accumulator style. So there are differences. But the reduce here is since it does assignment, you can assume that it does the accumulator. So we need to have a function and a sequence and an initial value. Let's do what we have done in scheme. What was then range? Initial thing. Let's see what's wrong. I need to have parentheses here. syntax error. Maybe we need to give proper function name or implementation. Let's see. Oh, again, yeah, I'm always going to syntax of brackets. Yeah, so that means because for this one for reduction we need two inputs. Do you think which one is list items? Which one? Do we have x and y? But one should be list item. One should be the accumulated value. Try. Or we can, in order to try, we can just do maybe a minus operation and 2. Yes? Yeah, this is the final. It's, yeah. Which one is accumulator? Yeah, because X is an accumulator, Y is the list item. It's the other way around we are used to have in a Rocket environment. Okay, do you have any question? So let's go back to what we had here. It was just a demonstration that you can apply the same principle in other programming languages. Even though what we have seen here is just the final implementation, you can apply design principle as well. So it will help you to improve your design in any other languages. Okay, thank you.